All right, so we're going to take a look at an example of binary search. And in order to start, we need some data. So I'm going to use this example array that goes from 10 to 60. And I'm going to draw it like this so we can see each cell. And here are the indices. Now, since we're searching, we need something we're trying to find. We need a goal. So our goal is going to be find 50 in this example. So I'm going to start out just by manipulating the array using some common sense. And from there, we will try and generalize what we're doing into a procedure that's always going to work based on where we are in the array. So initially, we look at this array and our length, we know it's 6. Now, because our length is 6 and we start at 0, that means our midpoint is just length, or we can just say it's 3. 6 divided by 2. 6 divided by 2 is 3. And so that's the first step in binary search. Find the midpoint and check out there. So inside the computer, this is what we see. We only see one cell. We know it's at index 3, and it has the value 40. And this is why the data has to be sorted for binary search, because we can't see the whole array at any one time with the computer. We can only see one cell at a time. But since we know the array is sorted, we know everything to the right is going to be greater than or equal to 40. And everything to the left is going to be less than or equal to 40. And so our goal is to find 50. Now, this means that since 50 is always going to be greater than 40, we can exclude this entire left-hand side, which is awesome. However, we do have a little bit of a predicament here. Looking back at our array, if we're excluding the indices 0, 1, 2, and 3, how can we keep track of that? One option would be to take 40 or to take 4 and 5 and put them in their whole new array. But if we have an array that's, 1 million elements long, that could get expensive really quickly in terms of memory. What I would advocate us try is let's keep track of where we are in the array. So instead of making a whole new array, we'll keep our array. But now, I'm going to do a dotted line. And the dotted line is sort of representing the part of the array that we have sort of chopped off. But now we have a variable, and this can be our start variable. And we'll also keep track of the endpoint. So start is 4, end is 5. And now, we've excluded everything here that has a dotted line. And so this is actually going to inform what our start value is. It's going to be the point that we excluded, the index that we excluded, plus 1. So it was 3 plus 1. And the reason why we're adding that 1 is so we can start at index 4 over here. So that would be index 2. If instead we had excluded the right-hand half of data, we wouldn't change our start point because that would still be the beginning of the array over here. But our end point would be the midpoint 3 there minus 1 over at 2. because we would be excluding that portion. So start is 3 plus 1, and that comes from this midpoint, adding 1 over to get to this still need to search data, starting at 4. Okay. Now we have 2 points or 2 elements here we need to check, 50 and 60. And let's think about how we're going to find the midpoint between them. I know it's obvious one of them is 50, and that's our goal. But just humor me for a moment. Because we can find the midpoint by maybe taking a look at, or let's start with finding the length. We know just by looking at it, our length should be 2. And so how can we get 2? The first thing I did try, is it the endpoint minus the start point? And well, that's 5 minus 4, which is 1, which is not 2. So where is this extra? Why do we have 1 and not 2? And so I think it's helpful if, see how our indices are written in the center there? I think it's helpful if we draw them more like a number line. So on a number line, we might have 5, 4, 3, 2, 1, and 0. And what we can kind of see now is that each of these numbers is corresponding to a box, much like our array. But even though this distance is 5, every number has a box except that 0. And so we need to add an additional 1, distance of 1, length of 1, to get the total length of indices 0 to 5. And the same line of reasoning applies for 4 and 5. We have 5 minus 4 right there. And in order to give 4 its position, we need plus 1. So that's where the extra 1 comes from. In general, length, the length of an array, starting at a start point, ending at an endpoint, both points inclusive, is the endpoint minus the start index plus 1. And that just sort of comes from this number line example. Okay, sweet. We found the length, which is 2. We found the length in general, which is very useful. And now, how are we going to get to the index 4? If we go back to our number line, we have some 0 point, and we have a start position and an end position. And we're trying to get to the midpoint. And our length, this is our length. We can't take the endpoint and divide it by 2 because that'll put us somewhere like right there. What we want to do instead is we want to first go the whole distance of the start. So we're working from this position. And then we want to go halfway from the start position, halfway of the length between the start and the endpoint. So this distance, which is L divided by 2. So start plus len divided by 2. And then substituting in the previous expression for length, we know that's going to be start plus end minus start plus 1, integer divided by 2. And now we can compute our midpoint. 4 plus 5 minus 4 plus 1 is 2, integer divided by 2. So our midpoint's now 5. And so let's check 5. In our computer, index 5 is the value 60. And so because of the fact that the data is sorted, everything to the right, it's going to be greater than or equal to 60, or in this case, there's no data there. And everything to the left is going to be less than or equal to 60. We're trying to find 50, so we can exclude all of that. So our stop position, here's 4, here's 6. We know it doesn't exist. But our stop position is then going to be given by 5 minus 1, because we're moving, because we know it's not this. So we're going to go over there, and our start is also over here. So now we are in a very desirable position, and that is our start value equals our stop value. Or I believe I should call this end. 60, 50, 60. Okay. There you go. And so our start value equals our stop value. And so really all that's left to do is to check this final position. And sure enough, 50 is indeed at index 4 in our array. If 50 was not there, we would return an error code indicating that we didn't find 50. But because 50 is there, we would probably want to return 4. And that way, given the same array, we have array of 4, that's going to show us how to get 50. So that's a little bit about binary search, and I hope this was a helpful video as far as what kind of ideas you can use to implement binary search. Notice, I would say, like, in particular, things like this midpoint calculation might be useful. And the idea of keeping track of the start and end values can be something that is applicable to an actual programming task. So good luck, guys, and thanks for listening.